I'm glad you're here. Check this out. I'm trying to ask this machine to identify my face, and when I click on this identify, it says unknown. Well, this machine doesn't know anything. Let's train this machine, and let's do it in a little supervised way, where I'm in the supervised learning. We have a label data, and input and output is paired. So basically this face's image was my input. So let's say my name is ABC. Okay, let's be ABC, enter qualification, MTech data science and engineering, and now let's train this. Okay, so it says face training completed, and now let me ask him, can you identify me now? And yes, see, it can identify me. It's giving my name, my qualification as I trained this machine. And also to note the accuracy out here. We will discuss about this later in this video. So let's get started. Well, we just saw supervised learning in a way, which is one of the type of machine learning. There's another type called unsupervised learning, which doesn't work on a label data, but it discovers and learns on its own. There's a reinforcement learning, which is more around trial and error method, and once the desired outcome is there, it is awarded, the model is awarded. So well, we are not going to touch unsupervised learning and enforcement learning today. Let's get into deep learning, where the face recognition, which we are trying, is there. So what is deep learning? Deep learning is a subset of machine learning, as you can see here, and that involves artificial neural network. Now, artificial neural network is very similar to our human brains, where one neuron in the brain receives the signal and it processes it and passes it to the next neuron. In a similar way, in the deep learning model, they are interconnected node known as neuron, which you can see here. Neurons are organized into layers. Since deep learning involves neural networks with many layers, hence the term deep is used. So you can see how there's interconnected nodes, the neurons, and their different layers. There can be multiple layers to it, 6 layers, 4 layers, and all that. So that we'll see later. So coming to our use case, very famous use case, face recognition has been there for decades. It has been always like nowadays, means face recognition is one solution that you see day-to-day life also. So in your day-to-day life, so first thing first, let's see the face here. So in the face here, you need to see there are lots of data points within a face. Okay, and there's a difference between the data points, like there's a distance between your eyes and nose, which will vary. Then there is distance between 2 eyes, and so on. So if you see these data points in a multi-dimensional space, and you will see this to be converted into a digital format, which we're gonna talk soon. So coming to face recognition use cases, there are 2 types of use cases. One is one-to-one, and this is where the success rate is very high. One of the example is your mobile face unlock system, where you train your phone or mobile with your face, and then later when you show up your face, it just unlocks the phone. So this is one-to-one, basically also known as verification use cases. Mostly supervised learning is there, where input and output parameters are mapped. Now another one-to-one you can imagine is a passport control at border, where you scan your passport, and it also captures your current image in there, and as soon as you scan your passport, it retrieves your e-passport where your pictures are stored and tries to match and compare your current image being captured and with the image that is stored, and if it all goes right, you get a pass-through. So that's one-to-one. Now one-to-many, also known as identification use cases, they can be, you can imagine one-to-one. When I say one-to-many, you can understand what it means. Like for example, airport security, it's one of the use case where there are lots of people in the airport, and should they be supposed to be there or not can only be decided once they are identified. So that's one thing. Another thing, you can imagine you're sitting at a gate waiting for you to be onboarded, and in the last minute, maybe you were sitting there for 3 hours, in the last 1 hour the gate changed. So there should be a system which identifies you at the gate and says, hey man, you're sitting in the wrong gate, so let's inform you and help you to get to the right gate. So this can be, so you can imagine any use case to identify a person from a group of persons. So that's one-to-one, one-to-many use case. Our sample solutions and what we're going to demo is around this, which we will see later. Well, again, to be said, I like this image. I have taken it from free pick, and they asked me to put it there if I want to use it for free. Okay. When I talked about digital format of the face, this is what you need to understand. Where data science is, maths is there. Okay, all the solutions, most of the solutions that you see within data science, it's around maths. So what mathematical concepts we're going to talk today? It's vector. So vector is a mathematical entity which has both magnitude and direction. This is what we learned in schools. And today we're gonna implement in machine learning where it can also represent data points, weight, gradients, etc. So in regards to face recognition, where what we have to do is, as a practical application of vector, during enrollment phase, what we do, we capture the face image of a person and generates the corresponding feature vector of it, and store this vector in a database along with the person's identity. This is exactly what I was doing when I was capturing my face. I'm actually storing it as a vector, and I'm also telling who am I and my qualification. So, and when during recognition, as you saw when I was saying identify, what it does, it again captures my new face image, generates a feature vector, and compares it against the stored vector in the database. And again, if you remember, there was some accuracy. So there's some threshold that you have to keep. Beyond that, you will say, okay, I'm highly confident that this face match, and this face is for this particular data or whatever information you have. So this vector, if there are lots of deep learning models in the market right now. One is FaceNet, developed by Google, and the FaceNet model is the output of the FaceNet model is a fixed size vector, typically 128 dimension for each face image. So if you have seen this models, much deep learning models, there is a vector inside. Deep Face, again by Facebook, that's also stores images in vector, and this is 9-layer deep neural network trained on large data set of labeled face images. So, and then there's an arc face from Microsoft. Again, the embeddings are 512 dimensional vectors, but the size can vary on the model architecture. Okay, now we understand what is our digital format of the face. Let's see how we compare. So to compare, we have two mathematical formulas out here. One is cosine similarity and another one is in Euclidean distance. So to verify if two face images belongs to the same person, we normally compute the cosine similarity or Euclidean distance between their embeddings, which is vectors. So what we in a demo, what you saw in the demo, and what we have done is, I've used cosine similarity. So let's see what is cosine similarity. So there are two vectors, A and B. The vector B is the trained data, which is already there and sitting in the database. Your new image that is captured, or new face image that is captured, is converted into a vector A. Now with two vectors, what we do, we calculate the cosine similarity. So cosine similarity will be a dot product of these two vectors divided by the magnitude of those vectors. So when the cosine similarity is very close to 1, if you remember the accuracy, that was nothing but a cosine similarity, which was around 0.96. If I remember. If you don't, you can always rewind the video and see that. So it was around very close to 1. Then we say, okay, there is a similarity, and we can predict it with some confidence. It should be this person. Okay, if the cosine similarity will be -1, means it's completely dissimilar. Okay, and if it's close to 0, means indicating low similarity. Basically, cosimilarity values vary from -1 to 1. Okay, so this is what the mathematical concepts around what we are doing. Now, using these concepts, you can have your own implementation. The concept remains the same. In our sample implementation, what you saw, I'm using this, which is a Python 3.11 with all the dependent packages like OpenCV, NumPy, Elasticsearch, face recognition, okay, Swagger client, which we'll see later. So that's there. Then I'm using Kivy and Kivy Material Design. The app that you saw was designed in Kivy. It's an open source Python app development framework, which is cross-platform. It works cross-platform, and means you can, if you are an iOS developer, you can use your iOS Xcode and to develop those mobile application, or an Android, or any cross-platform to actually develop an mobile app. For that reason, being a Python fan, I like Kivy, so I'm using Kivy here. Second, Elasticsearch and Kibana. Okay, Elasticsearch has grown over the time. There is a licensing also has changed, though to my knowledge, storing vectors and querying the vectors, there is no such license requirement. The basic license of Elastic should work, which allows you to do, but there is again the machine learning features and all, which needs an extra license. But anyways, it's always good to check licenses before you use it. Okay, in the sample implementation, this is the sequence diagram. You saw the two apps. Each one has its own flow. The first one, the training app, where it captures the images from the mobile app, calls an API gateway, and the API gateway calls the training services. Basically, that's training services again. It's all about Python, so I'm using Python Flask. It reaches that Python Flask server, and then that Python Flask server is saving this information to Elasticsearch. Again, when we try to identify it, follows the same path and returns you the result. Okay, so let's see what we have here. Okay, so if you see, I have the services are designed for, like the service that you saw for training and recognition. There is a Swagger. There's an open API specification that I have used to design my two services, and from here you have an ability to download a Python client, which you can use in your Kivy app, and also you can generate a Python Flask implementation. so where where the services can run. So this is where it is. Then I have Elasticsearch. I have created one index called face recognition, and if you see here the mapping, there is a field called face vector, which is a type of dense vector, and then it's storing my first name and other relevant information. So when right now if I did one query, so when I'll search this index, this is the face vector that was like the image that was captured was converted into this face vector, and this is the vector that was stored. Okay, and coming to the code, there is a lot to it. Probably if you like it and if you want to see this code, write me a comment. I'll point you to my GitHub repository where you can get this code. But at high level, it connects to the Elasticsearch node here, and it does the cosine similarity, and this is where, and it is returning me the results. So this is what it is. There's a Kivy setup, like there's a lot of things. There's a Kivy. I have used the .kivy file for my design. So requirement wise, these are the requirements. I'm running a Flask server. So this is my controller where you saw the code, and these are the requirements. Check out for this connection. Most of the time it needs the lower version of it and all that. But in any ways, if you want to do this sample implementation, and if you want the code base of it, do write me over a comment, and I will help you with my GitHub link. Okay, thank you for watching, and I see you in my next video. Till then, you take good care of yourself. Thank you. Bye-bye.